Now we come to the testing and debugging part. So what we are going to see in this session is important concepts pertaining to program testing, then about black box testing, equivalence partitioning and boundary value analysis. Then we'll talk about white box testing, debugging, then unit integration and system testing, and then we'll summarize. So how do you test a program? You input test data to the program and you will observe the output, and you will just realize whether the program behaved or program executed in the manner in which you might have expected. So you'll provide some input and to the system, to the software you have made, and then output you will try to realize. So this is what happens in your testing, in a broad view. If at all the program does not behave as expected, and this is going to happen quite often, we will note the conditions under which it misbehaved or it failed, and then we will try to debug. Debug means D and bug. Bug are the problems and D means removing these bugs, and we will try to correct it. So a failure, let us see the distinction between error, faults and failures. So failure is a manifestation of an error. That is, we also know error as defect or bug. Error, defect or bug, that is why we call it as D error, D defect, and in good word, debug. So a failure is the manifestation of an error, and just a presence of an error, it does not say that the software is going to fail, but there is an error. Then what about fault? Fault is an incorrect state entered during program execution. So it is different from error in the context that this is talking about an incorrect state resulted with some program execution. For example, a variable value is different from what it should be. This can be a result of a fault, and also a fault may or may not. We have seen in error also that presence of error may not lead to a failure. A fault may and may not. It may lead to a failure, but it may not. So test cases and test suite, this is generally asked in interviews. How do you generate test cases? What are test cases? What are test suites? So test a software using a set of carefully designed test cases. And most organizations, just after they complete their requirement analysis and specification, they tend to create these test cases. On the basis of these test cases, the software is tested. So there are always opportunities to create or design good test cases. The set of all test cases combined, we call them as test suites. So a test case is what? It is a triplet. What triplet? I, S and O. I is the input, is the data input to the system. S is the state of the system. It is the state of the system at which the data will be input. And O is the expected output of the system. So input, data input, state at which the system will be given an input, and the expected output of the system. So this is what test case is all about. Then an important question comes, generally people say verification of the system, validation of the system. So there is a difference between verification and validation. Verification is determining, the process of determining whether output of one phase of development conforms to its previous phase. Okay. Validation is the process of determining what? That once the system is developed fully, it conforms to its SRS document. So verification means whatever you are doing, if 2 plus 3 has to be 5, it has to be 5. But it does not tell that the customer has asked not 2 plus 3, but he has asked for 2 into 3. Okay. And this is checked in validation. So verification is whether you are making the product right. Validation is whether you are making the right product and how you are going to signify the right product. And this can only be confirmed when it conform or comply the SRS document. So verification is concerned with the phase containment of errors. Containment of errors at different phases of your software lifecycle. While the validation aims at final product to be error free, if it conforms to the SRS and error free, then we say we have done validation. Then we come to an important aspect, that is designing of test cases. So you cannot test. It is very difficult for any non-trivial system to be tested. This is quite impractical because the input data domain is quite large. You cannot test with each and every input data. So we design an optimal test suite for it will be of a reasonable size and it will uncover as many as error which could be. So it uncovers or resurface the errors which are possible and many of them. So designing of an optimal test suite means reasonable size and uncovering the errors as possible, as many as errors as possible. So if we select these test cases randomly, okay, if we randomly test or select the test cases, then various test cases would even not contribute to the significance of the test suite. Means they will not actually check or verify what we wanted to do, and they will also not detect errors not already being detected or by other test cases in the suite. So these are the issues with randomly selecting the test cases. The number of test cases in a randomly selected test suite is actually not an indication of effectiveness of testing. So testing a system using enormous amount of randomly select test cases, it again does not mean that many errors in the system will be uncovered. So just saying that I have made n numbers of test cases and I have tested with it, this does not guarantee that the errors have surfaced or they are uncovered. Just consider an example of finding the maximum of two integer x and y. Simple code is there. If x is greater than y, max is x, else max is y. This should be y. So the test suite will be x equal to 3, y equal to 2, and x equal to 2 and y equal to 3. This can detect an error. Easily it can detect an error that it is whether it is giving a maximum 3 or 2. But you can have a larger test suite like 3, 2, 4, 3, 5, 1. So this does not detect the error. Okay. So a large test suite does not guarantee you that it is going to detect error. But a carefully taken test cases or test suite will definitely do that. So now we know that we need to have a systematic approach, or there has to be some systematic approaches which are required to design an optical test suite. And each test case in this suite, because a combination of test case is only test suite, so each test case in this suite should detect different errors. Test cases should not be like that they are identifying only similar errors. So test cases should detect different errors. There are two main approaches to design test cases. So people talk about black box testing and white box testing, but actually black box approach and white box approach, we also know white box by glass box. Black box and white box approach, they are the approach to design test case, right? So if you are asked, how do you design test case? Don't start by ISO. I gave some input and output. What was the state? But actually the person is asking you about black box and white box at that point of time. So black box testing, the test cases are designed using only functional specification of the software. Functional specification, because black box means this is a black box and software is inside it and you don't know what is inside. And you are not aware or you don't have any knowledge of the internal structure of the software. That is why this black box testing is also termed as functional testing. While on the other hand, the white box testing, when we design white box test cases, it wants or it requires you to have the internal knowledge or internal structure knowledge of the software. That is why, because we are bound to know the internal structure of the software or the product. That is why white box testing is also known as structural testing, right? So for designing black box test cases, there are essentially two main approaches. One is your equivalence class partitioning and boundary value analysis. Equivalence class, you know that in mathematics we have learned that if a class or if a set is reflexive, symmetric and transitive, then it is an equivalence set, and the same criteria applies here also. And in boundary value analysis, the containment of error or the problems occurs always on the boundary. Means 0 to 100, you check for 0, you check for 100. This is termed as boundary value analysis. So let us see them in detail. Equivalence class partitioning. So input values, they are partitioned into equivalence classes, as I just suggested what equivalence class mean. So partitioning is done. We have various inputs. You partition them. In a way that program behaves in a similar way to every input value belonging to an equivalence class. If this is an equivalence class, means this class has some input, then program should behave to each and every input of this one class of equivalence partitioned class in the similar fashion. So why we are required to define an equivalence class? Just test the code with just one representative value from each equivalent class. Why to create a large test suite? As I suggested, that large test suite is not the criteria of uncovering the errors. So as good as testing using any other values from the equivalence classes. So if you have an equivalence class, you partition it carefully. You can just take out one value and just check it. So how do you determine the equivalence classes? You examine the input data, and there are general guidelines for determining the equivalence class which can be given, and this only is related to the reflexive, symmetric and transitive criteria that this set is following or that this partition is following. For example, if the input data to the program is specified by a range of values, say for example numbers between 1 to 5000. So one valid and two invalid equivalence classes are being defined like this. 1 to 5000, these are all valid, and beyond 5000 invalid, and before 1000 they are invalid. Okay, that is how we define it, because in this number line, is sort of number line, you can see that valid portion is this, invalid portions are this and this, left and right. So if input is an enumerated set of values, for example ABC, one equivalence class for valid input values, another equivalence class for invalid input values should be defined. So not only defining the equivalence class, but defining equivalence class for valid input values and invalid input values, they need to be defined. This is very important. For example, a program reads an input value from 1 to 5000. We compute the square root of the input number. What is the input sqrt? So there are three equivalence classes. First is a set of negative integers, set of integers from 1 to 5000, and integers which are beyond 5000, that is larger than 5000. So now we have three equivalent classes. Negative, these are two invalid, and the middle one is the valid equivalent classes, right? This is how we define it. So a test suite must include, if we perform or if we choose equivalence partitioning for this type of testing, which was our black box testing. So a possible test suite can be -5 invalid, 6000 invalid, and 500, which is inside 1 and 5000, that is a valid input. Okay, so this is what we have discussed about testings, the approaches, and finally the black box equivalence partitioning. We will be covering more in later session. Thank you so much. Take care.